because Gilman reagents are particularly good at reacting with alkyl halides. Grignard reagents, we saw previously, reacting with carbonyl groups. So, when you want to form a bond with an alkyl halide, you use Gilman reagent. And again, we're going to look at the two materials and determine that's a nucleophilic carbon, that's an electrophilic carbon, because of the polarization of those bonds. So there's going to be an attack from the nucleophilic carbon onto the electrophilic carbon, kicking off the iodine, and the product of the reaction is this. There you go. So we have formed a carbon-carbon bond. Much like the Grignard reagent, the difference here is that we're forming a bond with an alkyl halide as opposed to ketone or an alkyne. And I chose the colors of the bonds very carefully because, again, people tend to screw up here when it comes to adding or subtracting carbon. The new bond is the one shown in baby blue. So if we count out 1, 2, 3, 4 bonds on the black piece, then we know we have the correct number of carbons. And then if you switch to the red, you can count 1, 2, 3, 4. Oh, sure. See what happens? It happens to everyone. So I still, to this day, number the carbon chains to make sure I don't add too many. Any questions about that? Yes?
We know that two alkyl groups are attached to copper, and the forces are acting in opposite directions, and they are the same forces. Wouldn't these forces cancel out each other?
In terms of the overall polarity of the molecule, yeah, they might cancel out, depending on the direction of those two alkyl groups on the copper, right? So they could be in this direction and they don't cancel out. But we're not looking at the overall polarity of the molecule, we're looking at the overall polarity of that bond to describe the reactivity at that atom. Okay? Great question. Yes?
Do we have to balance the equation?
We do not have to balance the equation. So some people will say, but there is 2 of these long butyl chains for every one of these. So in reality, you only need to use 0.5 equivalents of copper experimentally to 1 equivalent of this, because there are 2 nucleophilic chains of copper. We're not going to worry about that. These questions are going to be phrased mostly as just predict the product. You don't have to worry about balancing the equation or side reactions or anything like that. Oh, great question. What happened to the iodine and the copper and the lithium? Those just form copper iodide, and I think, let's see, lithium and copper. Yes, lithium cuprate. No, there's not enough iodide around. There's too many lithiums. No, there's not. Lithium iodide. Yeah, so if you're worried about balancing the equation, I think that's it. Or make some kind of lithium cuprate iodide salt or something. Yeah? Don't need to write. So I didn't write it on the page because it's not important. Organic chemists were concerned with carbon-carbon bonds that we're making, period. The fact of the matter is those salts, the copper salts, the lithium salts, they just wash away in the workup anyway. So experimentally, they're of no consequence. So when I say predict the product, I'm referring to the organic product. Any other questions about this? So to simplify this as much as I can, all you do is you connect the 2 chains with a bond. That's it. So let's take a look at the next 2, and I'll actually make it into an in-class activity. Go ahead and take a few minutes and draw out the product of these bond-forming reactions. There you go. So I drew out the two pieces beside each other because they're going to form a bond between each other. I've numbered them to make sure that I have the correct number of carbons. Now all I'm going to do is add a bond between them to signify the two electrons that are forming that bond. Pretty easy stuff, right? Questions? Let's move on to the review already. All right. So, these are very versatile reactions for forming carbon-carbon bonds and building up carbon-carbon skeletons. And on the exam, we're going to have synthesis problems where you do have to build your own molecules. Yes? Yes. Just make sure it's the same place. So if you have a methyl group in one, put a methyl group in one. Oh, yeah, okay, so same thing. Methyl group on one, methyl group on one. The nucleophilic carbon is the one attached to the copper. The electrophilic carbon is the one attached to the bromine. So you just have to make sure that you connect those two carbons. Any other questions? Okay, so one more quick in-class problem. Which of the following molecules will not yield the desired organolithium reagent when treated with lithium in pentane? All right, we'll give everybody maybe 30 seconds to try to figure this one out. As a hint, if you haven't figured this one out yet, the organolithium compounds are excellent nucleophiles and also good bases. Another 30 seconds. Okay, so I've drawn up the three that will form the desired alkyl lithium intermediate. Those are very unstable. They're all right if you keep them in a flask, but there's no reason for those molecules to do anything after the alkyl lithium forms. What's the problem with 4-bromo-1-pentanol? Anybody? That's right. The alcohol on the molecule is an acidic hydrogen. So, if I convert this into the corresponding alkyl lithium species, it's going to make this, and then immediately, what will happen is that nucleophilic carbon is going to deprotonate the alcohol. So if I throw this molecule into lithium to make an alkyl lithium, I will make, oh, running out of room, that. Because I have self-protonate. Questions about that? So, just a reminder, when you're making these Grignards or these Gilman reagents, these highly nucleophilic carbon molecules, you want to keep acidic protons away, not just in the solvent, but in the reagents themselves. They can't have easily removed protons. Yes? Where'd the lithium go? The lithium is a plus, so it's, actually, you know what, I'm just going to draw on this slide. That's where the lithium goes. It works as a counter, okay? erase this now. All right, so very briefly, we're going to end talking about oxidation reduction chemistry. You might have learned some acronyms in high school. Leo the lion says GER, stands for Leo GER. So losing electrons is oxidation, gaining electrons is reduction. I've never heard that one before. The one that I was taught was Euler. Euler, oxidation is loss of electrons, reduction is gain of electrons. Does this ring some bells?